Thanks for clicking on Total Harmonic Distortion channel. Today we're going to take a look at a free version of the software I'm making available in the description below. First we're going to take a look at the noise floor tab. This measures the noise floor of any device plugged into your audio interface, and also measures the noise floor of the audio interface itself. It sort of mixes everything together, which is a problem with these kind of testers, but there's really no way around it. But we'll go into that later. First off, it comes up running at 48 kilohertz. If you have an interface that supports higher sampling rates, you can choose one of these different rates. It'll show up no matter if your interface supports it or not. It just won't allow you to select it. Okay, so this is the noise floor at 192 kilohertz. It does raise the noise floor of the interface itself. Now I'm going to take a look over here, and this is basically chooses what we're taking a look at, the different channels. The gray channel is a loopback channel. It's just basically a channel that kind of loops back from the input to the output right on the interface itself. I use that as a reference. So this is the noise floor of the interface itself. It's in channel 4. And then this is the noise floor of the device under test, which happens to be this Nuremberger. As you can see, there's some noise on the upper frequencies in this pedal, but this is beyond human hearing. Everything that's in the red zone is above 20 kilohertz. Everything in black is below 20 kilohertz. But anyways, the reason why I chose this pedal is because it suffers from a problem common with a lot of pedals, and that's jitter in the sampling clock. Now, when you jitter sampling clock, you end up seeing something along this line, something that looks like this. Basically, you see a lot of high frequencies above Nyquist. And this is basically caused by a clock jittering back and forth. It's not a really nice cadence on the clock, so it jitters around because of a bad PLL or using a RC oscillator or whatever. But I do see this in quite a few effects, so I just wanted to make people aware of this. Now if we go over to the MLS tab, which will basically just show us more of a frequency response, you can see in the frequency response of the pedal, it pretty much goes away. There's a little bit of a hump there, but compared to the noise floor, it just really boosts it. It's just kind of the test just really exacerbates this problem. Anyways, let's go on to a different tab. Next up is the impulse response tab. I'm going to turn off our channels and only look at the generation channel. So we're only generating a single pulse on the output, and we get back on the loopback channel as this particular set of squiggles. If you're interested in why this happens, look into half-band filtering, CIC filtering. It's a little beyond this video. But suffice to say, you send a single sample out, you get a squiggle back, which represents this curve right here. Basically, you can't, an audio interface can't generate anything above half its sampling rate, so it has to filter out anything above that. This can also show the frequency response of any device under test. But there's some caveats to this. There's not a whole bunch of energy in an impulse response. It's a very quiet signal. So it leads to some weird results. Like you can see this thing go up and down right here. And that's basically happening because the sampling rate in this unit does not match the sampling rate of my audio interface. And because they're just slightly off, it's going in between different samples, and you'll see this kind of thing happen. And that's something that'll show up mostly in an impulse response because of the way they work. Every test has some advantages and disadvantages to it, so I'll leave it up to the user to figure out what works for them. The next tab we're going to take a look at is the RNG tab. It uses a random number generator to generate white noise. And you can see on this, the loopback channel itself goes all the way up to 96 kilohertz-ish, and then the zoom itself only goes up to a little above 20 kilohertz because it samples at a slower sampling rate than the 192 kilohertz we're doing on the audio interface. But anyways, I'll take a look at this. Now, if you grab anywhere on the meters, it'll adjust the volume going out, which is useful because a lot of pedals, especially the distortion pedals, need quite a lower gain signal, and this is a way to compensate for the volume of the pedal. So just grab that anywhere, and it can move it around. Okay, next up, I guess we'll take a look at the MLS tab. This is another noise tab, but rather than using a random number generator, it uses an MLS signal. MLS signal is basically a signal in purple. So it's basically a signal that only consists of +1 or -1, or positive 0.5 and negative 0.5 in this case, because I'm negative 6 dB down. But anyways, it's useful because this particular signal produces exactly a flat response on the FFT. As you can see, on the loopback channel, it shares the same impulse response with the actual impulse measurement. It's just another way of getting an impulse response out of a signal. But this has the advantage of it actually being quite loud, and because it only consists of positive and -1, you can do some crazy math on it. But anyways, in addition, there's a volume here, and on this particular thing, there's a compensate. Now, we'll turn off the purple because it's not working quite right. So the compensate is basically compensates for the volume. So say you want to test the pedal, and it distorts way up here, so you want to test it at a very quiet signal. The compensate will basically show you the whole signal, and it just compensates for the volume. So you scroll up and down, and it goes up like that. There's some additional features that we should probably talk about on this particular tab. First off, if you grab the FFT anywhere on it, you can click and drag it up and down, which is kind of useful. The mouse wheel zooms in and out, and you can pretty much drag in these to wherever you want. And this is pretty much the same for all the tabs. Pretty much all the tabs will do the same thing, where you can move things around. And they are persistent. But I guess other than that, we should probably take a look at the final tab, the sine tab. The sine tab simply generates a sine wave depending on where you click on the FFT. And there's also a compensate to compensate for your any volume loss that you digitally do on that. Now, it should be noted that I quantized the frequency to the nearest FFT bin. So when you have a lot smaller FFT sizes, say 2K, it prevents this kind of lobing. This particular plot is showing a frequency in between two FFT bins because we just dropped to a lower frequency and there's less of them. But once it clicks onto the actual FFT bin, it'll give you a nice impulse on the FFT. Support in future versions of the software is going to be based entirely on my YouTube subscription count. So if I don't get enough subscribers, this is what's going to happen.